Question number 5. Use A for acid, B for base, and then Ca for conjugate acid and Cb for conjugate base for the following equation. What you're having here is what we call Bronsted definition. Bronsted, sometimes called Bronsted-Lowry definition of acid and base. And that basically says that an acid will donate protons, a base will accept protons or hydrogen ions. So what you need to do is just see what's happening to this reaction. Here we're starting with OH minus, and that one is changing to water, and basically that water means HOH, and you can see that we have added one hydrogen, and therefore because we are adding a hydrogen to that, it means that what we are starting here is a base, so that will be the base, and then it accepts proton to give you water, and always a base will accept proton and then it will become a conjugate acid. So water in this case will be the conjugate acid. On the other hand, an acid will lose a proton, so minus H plus, and then it will give you a conjugate base. So in this case, if you look at this structure here, it has an OH here, and here you have O minus. That means you have lost a proton. And because of that, this will be the acid, and then it loses a proton to give you a conjugate base. So we see that the answers are base for that, acid, conjugate base, and conjugate acid. Question number 6. Draw resonance structures. Anytime you ask for resonance structures, remember to use that arrow that faces both sides, and that shows resonance. And always you start from a region of high electron concentration, move into a region of low electron concentration. And if you look at this structure, this carbon here has a positive charge, and therefore it will be electron poor, and therefore that has low electron concentration, while this alkene has a double bond, and therefore it has higher electron density or electron concentration, and therefore we're going to start from the alkene moving to the positive charge. And because we're moving 2 electrons, we'll use a full-headed arrow, so like that. And when that moves, you're going to get a double bond between these 2 carbons, and the positive charge will be neutralized. So remember, we use a resonance arrow, and then we redraw that structure. And now we move the double bond here, and that leaves this carbon empty, and therefore that becomes a positive charge. So because it's electron poor, the positive charge has moved to that carbon. We can draw another resonance structure again by moving these 2 electrons that form the double bond to that carbon, and you end up generating a new resonance structure. Remember, we use the resonance arrow. Then I'm going to draw the backbone. Remember, the first double bond moved there, and now the second double bond has moved here, and that has left this other carbon electron poor, and therefore it will be a carbocation, have a positive charge. And those are the 3 resonance structures.